Hello everyone and welcome once again to MJ's Maths and Stats. That's MJ Magic Studio to you. I am your host, your host, and as usual in the host mode, Mohit Jain. Today is a master class of remainder theorems, which are special remainder theorems. This is the second master class. First master class is still to get recorded, and we would be getting it very soon. We would be getting it done very soon. So stay connected and enjoy the show. Enjoy it, do practice it, because you don't never know that where you would find these type of questions. So on this note, if you haven't subscribed to the channel, please do it right now and enjoy the master class. Let's start now. Okay, let's begin the show by revising what are Totient number, because we would be requiring that when we would be taking up the first two remainder theorems. Now, let n be any natural number and its prime factorization is something like p1 to the power a1 into p2 to the power a2, p3 to the power a3, where p is nothing but prime number. This is known as prime factorization or prime factor or prime number basically. So Totient number of any natural number n is given by n into 1 minus 1 by p1 into 1 minus 1 by p2 into 1 minus 1 by p3 and on. So like if we take an example of say 15. 15 is 3 to the power 1 into 5 to the power 1. So Totient number of 15 would be 15 into 1 minus 1 by 3 into 1 minus 1 by 5. That would be 15 into 2 by 3 into 1 minus 1 by 5, 4 by 5. So Totient number of 15 is 8. Actually, what is the use of Totient number? Link is there in the description. We have an entire video recorded already on what are Totient number and what are its uses. We are just revising how to find Totient number. Okay, now there is one more thing which we need to understand. The Totient number of any prime number is simply p minus 1. We can see like Totient number for 17. Now 17 is the only prime factor for 17. So that would be 17 into 1 minus 1 by 17. Which would give us what? 17 into 16 by 17. That is nothing but 16, which is actually 17 minus 1. So, Totient number for any prime number is p minus 1, and this is how we need to calculate Totient number, which we would be requiring when we will be starting up with the next remainder theorem. So, the first one to start with is Euler's remainder theorem. And it is a very simple theorem which says that when x to the power t is divided by y, remainder is always 1. Now what is x, what is y, and what is t? X, y are coprimes and t is the Totient number of the divisor, that is y. If x to the power t, where t is the Totient number of the divisor, is divided by y, where x and y are relatively prime number or co-primes, then remainder is always 1, and we accept this remainder theorem as it is without proof and use it. Like I'll take few example. 13 to the power 18 is divided by 19. What is the remainder? We can see first of all that 13 and 19 are co-primes and 19 is a prime number. That means Totient number of 19 is 19 minus 1, 18. That means this particular thing fits in with Euler theorem. Straight away we can say that remainder is 1. Just we need to check whether it fits in the theorem or not. If it fits in, just use it. Like for record, you can keep one more example. 13 to the power 6 is divided by 9. 13 and 9 are co-primes. Done. First check done. Now we need Totient number for 9. 9 is just 3 square. So Totient number for 9 is 9 into 1 minus 1 by 3. That is 9 into 2 by 3. And bingo, that is 6. Which fits in here. So this is of the form x to the power t divided by y, where t is Totient number of y. We can straight away say that remainder for this is 1. Let's take a few more examples. 7 to the power 8 is divided by 15. Try it. We have got 2 points check. First, x and y should be co-prime. 7 and 15 are co-prime. Checked. Next, we need Totient number of the divisor. So 15 is 3 to the power 1 into 5 to the power 1. Totient number of 15, we have already calculated this earlier, is 15 into 1 minus 1 by 3 is 2 by 3. 1 minus 1 by 5 is 4 by 5. That happens to be 8 and it matches. If the format matches with x to the power t by y, we can say directly remainder is 1. Now please give this a try. 13 to the power 32 is divided by 15. Pause the session and try it. Okay, you must be having the answer by now. 13 and 15 are co-primes. Check. Totient number of 15 is 8. But here is 32. But we can see that 32 is multiple of 8. So this question can be written as 13 to the power 8 whole to the power 4 is divided by 15. Clear? That means 13 to the power 8 is divided by 15 once, 13 to the power 8 divided by 15 twice, thrice and 4 times. And every time it will leave remainder 1. So remainder would be 1 to the power 4, that is 1 again. So we can say that x to the power t whole to the power n when divided by y, where x and y are co-prime and t is Totient number of y, in this case also remainder will be always 1. Let's try one more. 13 to the power 99 is divided by 17. Find the remainder. Give it a try. Okay, let's go for the check. 13, 17 are co-primes. Check. Totient number of 17 is 16 because 17 is a prime number. And Totient number for any prime number is p minus 1. But this is 99. Now can I write 99 as 16 into 6 is 96. Okay, it's 96 plus 3. That is 16 into 6 plus 3. So 13 to the power 99 can be written as 13 to the power 16 whole to the power 6 into 13 to the power 3. This is divided by 17 and again this is also divided by 17. The first part falls into the format of x to the power t whole to the power n divided by y. In that case, remainder is 1. So remainder for the first part is 1. Bingo. We are done with this. We just need to find remainder of the second part and then we'll multiply both the remainders. Now 13 to the power 3 means 13 into 13 into 13. Now it is divided by 17. This will give residue minus 4. This will give residue minus 4. This will give minus 4. So remainder is minus 4 into 4, 16 into 4, 64. But remainder cannot be negative, we know that. So we need to keep on adding with the divisor till we get a positive remainder. So 17, 34, 51, 68. If I add 68, which is nothing but 4 into 17, I would be left with 4. So remainder of 13 to the power 3 divided by 17 is 4. Remainder of first part is 1. So final remainder is 1 into 4, that is 4. So when 13 to the power 99 is divided by 17, remainder is 4. Good. Now do one more. 7 to the power 2112 is divided by 90. Find the remainder. Give it a try. Okay, let's go for the check first. 7 and 90, okay, are co-primes. Done. 90 is 2 into 45, 5 into 9. So the prime numbers or prime factorization is there. Totient number of 90 would be 90 into 1 minus 1 by 2 is half. 1 minus 1 by 5 is 4 by 5. And 1 minus 1 by 3 is 2 by 3. 10, 3, 3 into 6, 8 into 3 is 24. So totient number of 90 is 24. But here power is 2112. Let me divide 2112 by 24. 2 times 12, 1056. Then this will be 528. I'm enjoying the process. 264, 10, 12. Yes, 88. It will go 88 times. So this can be written as 7 to the power 24 whole to the power 88 is divided by 90, and this is in the form of x to the power t divided to the power n divided by y. Then according to Euler's remainder theorem, remainder is straight away 1. Remainder is 1. Let's do one more, 7th example on this. 7 to the power 2115 is divided by 90. This is on the same lines we have done it earlier. Pause, do it yourself. So the question is on the line we have done in question number 6. 7 and 90 are co-prime checked. Totient number of 90 we have calculated, but we need to calculate if this is a new fresh sum in front of us, that is 24. And 2115 is actually 24 into 88, that is 2112 plus 3. So this would be written as 7 to the power 24 whole to the power 88 into 7 to the power 3. And this is divided by 9 will leave remainder 1. This when divided by 90, let's see, remainder would be how much? 7 cube is 343. 343 is divided by 90. So 90 into 3, 270. 343 minus 270 will give 73. So remainder would be 1 into 73. 1 into 73 for the second part. The overall remainder is 73. Let's do one more quickly. Find the remainder when 12 to the power 14 is divided by 13. This question can be easily treated with help of our arithmetic algebraic rule of factor theorem or remainder theorem. Let's see whether how it fits in Euler theorem. 12 and 13 are co-prime checked. Totient number of 13 is 12. Clear. As 13 is the prime number, totient number is 13 minus 1, 12. So, but this is 14, so 12 to the power 12 when divided by 13 will leave remainder 1. We are left with the 12 is square, which need to be divided by 13. So this portion falls in the remainder theorem, that is 1. 12 into 12 divided by 13. 12 when divided by 13, we get a remainder of minus 1, that is residue of 1. Here also minus 1. Minus 1 into minus 1 is 1. So eventually, final remainder is 1 into 1, 1. Now what is this negative thing? I hope you understand this, that any divisor is equals to remainder plus residue. So if 12 is divided by 13, if I say remainder is 13, then how much will be the residue? Residue will be 1. So residue is used with a negative sign. That means 12 are the extras with it and 1 is the deficit. So if 1 is given to number 12, it will be divisible by 13. For that we use a negative sign. For remainder we use plus sign. For residue, will shortfall or deficit we use minus sign. It always helps us in calculating these things in no time. That's why majority of the time I go for residues. If the number is very close to the divisor, always try to calculate residues instead of remainders. Let's take up one more, the last one for Euler remainder theorem before we move into the next theorem. 13 to the power 14 is divided by 15. Find the remainder. Okay, so I guess you have the answer by now. 13, 15 are co-prime. Checked. Totient number of 15 we need to find, that is 8. Done. But this is not 8, this is 14. So it is 13 to the power 8 when divided by 15. This part will give remainder 1. Now we have 14 powers, this is power 8, that is 6 powers. Now 13 to the power 6 is divided by 15. We can see that when 13 is divided by 15, residue we get is minus 2. So remainder here would be minus 2 to the power 6. Now minus 2 to the power 6, even power will be positive sign with 2 to the power 6 is 64. Now we can divide 64 by 15 once again to find the final remainder. 64 when divided by 15 leaves remainder 4. So final remainder is 1 from this part multiplied by 4 from that part. Final remainder would be 4. Please go through the entire questions once again to get a grip on Euler's remainder theorem. X to the power t when divided by y, where x and y are relatively prime number and t is the totient number of y, that is the divisor, remainder is always 1. The next important remainder theorem in our line is Fermat's little theorem, which is nothing but extension to Euler's remainder theorem. X to the power t when divided by y will leave remainder 1. This was our Euler's remainder theorem, where x and y are co-prime and t is the totient number of y. If I replacing y by any prime number p, then this will become x to the power p minus 1 is divided by p. We know the totient number for prime number is p minus 1. So if x to the power p minus 1 when divided by p will always leave remainder 1, and this is Fermat's little theorem, FLT. That's it. X to the power p minus 1 is equivalent to 1 mod p. That is, when x to the power p minus 1, when x to the power p minus 1 is divided by p, remainder is always 1, given that x and p are co-primes. Like if we see in example, we'll also do few example for this theorem. 3 to the power 4 is divided by 5. Now 5 is a prime number, check. 4 is totient number of 5, check. 3 and 5 are co-primes, check. We can straight away say that remainder is 1 according to Fermat's little theorem. Let's solve few more examples to get a grip on this. 11 to the power 12 is divided by 13. We need to find the remainder. We need to go for the check. 13, the divisor, is a prime number. Checked. Power is the totient number of 13. That is nothing but p minus 1. Check. 11 and 13 should be co-prime. Check. Then 11 to the power 12 when divided by 13 will always leave remainder 1. Let's take up one more. 3 to the power 5 is divided by 5. Now, our first check, divisor is a prime number. Power should be 5 minus 1, that is 4. but it is 3 to the power 5. 3 and 5 are co-prime. Done. So I can write this as 3 to the power 4 into 3 to the power 1, and this is divided by 5. This is also divided by 5. First part follows Fermat's little theorem. Remainder is 1. Second part, 3 to the power 1 when divided by 5 will leave remainder 3. So overall remainder is 3. Done. Now from this we can arrive to one more extension of Fermat's little theorem. And what is that? That x to the power p when divided by p, remainder is x, given that x and p are co-primes. If x and p are co-prime, then x to the power p when divided by p will leave remainder x. How? We can write this as x into x to the power p minus 1. This portion when divided by p leaves remainder 1. So the first portion, x when divided by p, leaves remainder x, given that x is a smaller number than p. Obviously, if x is a bigger number than p, then we need to find the remainder accordingly. Okay, so x to the power p when divided by p will leave remainder x, given that x is less than p. We can use it now. So let's note few examples for what we have just seen, that when x to the power p is divided by p, remainder is x. Let us take one example. 11 to the power 13 divided by 13. 13 is a prime number. This is p. X and p, 11 and 13 are co-prime. We can straight away say that remainder is x. Remainder is 11 in this case. Straight away. Like, you may note 21 to the power 47 is divided by 47. 47 is a prime number. This is power is p, and 21 and 47 are co-primes. Straight away we can say that remainder is x, and what is the value of our x? 21. So remainder is 21 in this case. Let's quickly practice few more. 1001 raised to the power 56 is divided by 29. Find the remainder. Give it a try. Okay, let's see the checking. 29 is a prime number. Done. Now power should be p minus 1, that is 28. But it is given 56. We can see that 56 is 28 into 2, multiple. Done. Now 29 is a prime number. 1001 is actually 7 into 11 into 13. So no matching between 29 and 1001. That means 29 and 1001 both are co-primes. So co-prime check. Now power should be 28, but it is 28 whole square. That is fine. So we can write this as 1001 to the power 28 whole to the power 2 is divided by 29. This will obviously leave remainder 1 is square. That is 1 again. That means x to the power p minus 1 whole to the power n divided by p will also leave remainder 1. Okay, let's do one more. 1001 to the power 57 is divided by 29. Give me the remainder. Okay, extension to example number 6. We know everything. 29 is prime number set. 1001 and 29 are co-prime set. P minus 1 should be 28, but this is 57. So 57 is 28 into 2 plus 1. So this can be written as 1001 to the power 28 whole square. This is divided by 29. This will give remainder 1. Done. Into 1001 to the power 1 divided by 29. Now we can do the manual division. 29 1001. 3 times 87. Then we have 13 1. 58 116 4 times 116. 16 15 31. 15. We are left with 15. So remainder for this second part is 15. Remainder for first part is 1. So overall remainder is 15. Okay, let's take one last example for records for Fermat's little theorem, and please give it a try. You can pause the session and give it a try. 11 to the power 57 is divided by 17. Find the remainder. So I hope you have the answer by now. Let's see. What should it be? 17 is a prime number. Check. 11 and 17 are co-prime. Check. Now p minus 1 is 16, but it is 57. 57 is 16 into 3, that is 48. 48, 57 minus 48 would be 9. So this can be written as 11 to the power 16 whole to the power 3. When divided by 17, this part remainder is 1, according to Fermat's little theorem. This is multiplied by 11 to the power 9 divided by 17. We need to find the remainder of this. Now 11 when divided by 17 will leave residue 6, that is remainder of minus 6. So remainder would be minus 6 to the power 9. Now again this is a huge number which we need to divide it by 17 again. So if I take minus 6 out, I'm left with minus 6 to the power 8, that is nothing but 6 to the power 8. 6 to the power 8 is 6 square is 36. It can be written as 36 to the power 4. Now when 36 is divided by 17, residue we will get is 2. Sorry, remainder we will get is 2. 34, 36, remainder we will get is 2. So it would be 2 to the power 4. Now 2 to the power 4 is 16. So what we are getting is 16 into minus 6. Now when 16 is divided by 17, residue is minus 1. So ultimate remainder we are getting is minus 1 into minus 6. That is 6 for the second part. Bingo. It's all logic setup which we are doing with help of the factor theorem, which says that when fx is divided by x minus a, remainder is f of a. That's it. Or simply, when 36 is divided by 17, we are getting remainder 2. So here remainder would be 2 to the power 4. When 11 is divided by 17, we are getting remainder 11 or residue minus 6. So overall remainder or residue will be minus 6 to the power 9. So first part remainder is 1, second part remainder is 6, overall remainder is 1 into 6, 6, and that is our answer. Now let us summarize Fermat's little theorem, and what does it say? That a to the power p minus 1 when divided by p, where p is a prime number, a and p are co-prime, remainder is 1. Which extension we have seen that when a to the power p is divided by p, remainder is a, and we have one few more extension to this. A to the power p minus a when divided by p will leave remainder 0 automatically, because if a to the power p when divided by p will leave remainder a, then a minus a remainder will become 0. That is the very useful extension. Or a into a to the power p minus 1, I'm just rewriting it, minus 1 when divided by p, in this case also remainder would be 0. You can just keep this into your mind, and all other are the extension. It will take few more seconds just, but if you can remember the extension, it would be of great help and in saving time. Okay, moving on to the next one is Wilson's remainder theorem, and this is in case of factorials. It says that when factorial p minus 1 is divided by p, remainder is p minus 1. That's it. It is only applicable in case of factorial, and we just need to fit in. Now, but it is sure what is p? P is a prime number. P is a prime number. When we write P, it stands for prime number. So factorial 16 when divided by 17, we can see this is of the format 17 minus 1. Factorial 17 minus 1 when divided by 17 will leave remainder p minus 1. 17 minus 1, that would be 16. Straight away we can use by using WRT, that is Wilson's remainder theorem. Factorial 18 when divided by 19, straight away will leave remainder 18. 18 is 19 minus 1, so remainder would be 18. So let's do one more. For example, factorial 17 is divided by 19. What should be the remainder? Now, based on the previous logic of factor theorems and remainder theorems and what we have done, can I write this as 18 into factorial 17 is divided by 18 into 19. Now 18 into factorial 17 is factorial 18. Factorial 18 by 18 into 19. That is 1 by 18 into factorial 19 minus 1 is divided by 19. So factorial 19 minus 1 divided by 19 falls in Wilson's remainder theorem, where remainder would be 19 minus 1, that is 18. So final remainder would be 1 by 18 into 18. That will lead to 1. Very soon we would be publishing part 1 of remainder theorem, where all these texts would be again discussed for revision. So winding up with Wilson remainder theorem, it says that when factorial p minus 1 is divided by p, where p is the prime number, remainder is p minus 1, and it can be extended to when factorial p minus 2 is divided by p, remainder is 1, that we have seen in the previous example. Clear? So it says that p minus 1 factorial is equivalent to p minus 1 mod p, or p minus 2 factorial is equivalent to 1 mod p. Remainder is 1 when divided by p, and remainder is p minus 1 when divided by p. So this was Wilson's remainder theorem. We have done Euler's, we have done Fermat's, and we have done Wilson's remainder theorem. So we are left with one more remainder theorem, that is Chinese remainder theorem, which I would be taking up in my next session. Please go through it and go through the SCF LCM thing also. The link is there in the description below before going up for Chinese remainder theorem. So on this note, this is Mohit Jain signing off from MJ's Maths and Stats. That's MJ Magic Studio to you. I'll see you soon. Just keep studying this. Keep the review on SCF LCM before you touch Chinese remainder theorem. I'll see you soon.